Tylenol, autism, and the science of confusion. Why this question won't go away. Few medical claims spread as fast as ones involving children, pregnancy, and autism. One of the most persistent claims you may have heard is this: Tylenol causes autism. Tylenol, also called acetaminophen, is one of the most widely used medications in the world. It's often recommended during pregnancy because alternatives like ibuprofen or aspirin can carry known risks. So when people hear that something this common might affect brain development, fear spreads quickly. But science doesn't move by fear. It moves by evidence and context. To understand where this claim came from, we need to understand three things. 1. What the studies actually found. 2. What could theoretically happen biologically. 3. And why correlation is so often mistaken for causation. What the studies actually observed. The controversy started with observational studies. Researchers noticed that mothers of children later diagnosed with autism or ADHD were, on average, more likely to report acetaminophen use during pregnancy. That's an association, not a conclusion. These studies did not show that acetaminophen directly changed brain cells, caused autism, or altered genes. They simply showed a pattern. Exposure and outcome appeared together more often than expected. But observational studies have a critical weakness. They struggle with confounding factors, variables that influence both the exposure and the outcome. And pregnancy is full of confounders. The tempting biological narrative. Still, people ask, could there be a biological mechanism? Science always asks that question. So let's walk through the most plausible hypothetical scenario, not as proof, but as a thought experiment. A hypothetical chain of events. Acetaminophen works partly by altering inflammatory and pain signaling pathways in the body. It is metabolized in the liver, and a small fraction of it creates reactive byproducts that must be neutralized by antioxidants, especially glutathione. Now imagine this scenario. A pregnant person experiences frequent infections or chronic inflammation. Their body already has elevated oxidative stress. Nutritional status or genetics reduce antioxidant reserves. Acetaminophen is used frequently and over long durations. Exposure happens during critical windows of fetal brain development. In theory, this could slightly alter the balance of oxidative stress or inflammatory signaling. And inflammation and oxidative stress are known to influence neurodevelopment. This is the biological plausibility that keeps the conversation alive. But plausibility is not proof. Why inflammation changes everything. Now comes the part that often gets missed. People do not take Tylenol randomly. They take it because something else is happening. Common reasons for use: fever, viral or bacterial infections, chronic pain conditions, autoimmune flares, severe headaches or migraines. And here's the key point. Maternal inflammation itself is one of the strongest environmental factors linked to altered neurodevelopment. Fever during pregnancy, especially when untreated, has been associated with increased risk of developmental differences. Infections activate the immune system. Cytokines, immune signaling molecules, can cross the placenta. They can influence how neurons migrate, connect, and specialize. So when a study sees acetaminophen exposure, it may actually be seeing the fingerprint of inflammation, not the medication. This is called confounding by indication. The reason for taking the drug, not the drug, may be the real variable. Oxidative stress, marker or cause? Oxidative stress is another concept often mentioned in this debate. Oxidative stress means an imbalance between reactive molecules and the body's ability to neutralize them. It's involved in aging, inflammation, infection, and many chronic conditions. Some studies show increased oxidative stress markers in autism. But here's the critical nuance. Oxidative stress is not a cause unique to autism. It's present in hundreds of conditions. It may be a consequence, a parallel process, or a marker of underlying biology. When acetaminophen enters this conversation, it's often because it interacts with antioxidant systems. But again, only meaningfully when those systems are already stressed. This brings us back to the same question. What came first, the stress or the medication? What happens when studies control for confounders? When researchers apply stronger methods, the story changes. Sibling comparison studies are especially powerful. Why? Because siblings share genetics, household environment, and many social factors. If acetaminophen were truly causal, siblings with different exposure levels would show different outcomes. But when these studies were done, the association largely disappears. That suggests that family-level or biological factors, not the medication, explain the earlier correlations. More recent meta-analyses that control for fever, infection, and genetics reach similar conclusions. The strongest data does not support a causal relationship. So why does the claim refuse to die? Because it offers a simple explanation for a complex condition. Autism has strong genetic foundations and early developmental origins. That can feel unsatisfying, even frightening, because it means no single cause and no single fix. A medication offers a concrete target. But simplicity is not accuracy. And fear spreads faster than nuance. Here's the balanced conclusion supported by current evidence. There is no solid evidence that acetaminophen causes autism. Theoretical mechanisms rely on extreme or compounded conditions. Inflammation and illness are far more plausible contributors. Treating fever during pregnancy is often protective. Chronic or frequent medication use should always involve medical guidance. The risk of untreated fever is clearer than the risk of acetaminophen. What this teaches us about science. This story isn't really about Tylenol. It's about how science works and how it's misunderstood. Correlation is the beginning of inquiry, not the end. Biological plausibility invites research, not conclusions. And complex conditions rarely have simple causes. When we slow down, examine confounders, and demand better evidence, fear loses its grip. And that's how real understanding begins.